Hello students, welcome to AIPathshala.com, your #1 partner for NEET and JEE prep. Before we jump in, do me a quick favor. Hit that like button, subscribe to the channel, and share this with your friends. Okay, you ready? Today, we are diving deep into one of the most fundamental topics in physics, thermodynamics.
So let me start by asking you a question. Have you ever wondered if there's like a speed limit for how efficient an engine can be? I mean, could we ever build a perfect 100% efficient engine? Well, it turns out physics has a very clear, very definite answer to that, and it's all waiting for us inside this chapter.
Okay, let's dive into this. So what on earth is thermodynamics? Simply put, it's the branch of physics that explains the relationship between heat, work, and energy. You know, how the steam from boiling water can power a massive train, or how burning fuel in your car makes the wheels turn. Yep, that's all thermodynamics right there in action.
Now, our first stop is a bit of a funny one, the Zeroth law. Yeah, Zeroth. It got its name because scientists figured it out after the first and second laws, but realized it was actually more fundamental. It says that if system A is in equilibrium with system C, and system B is also in equilibrium with C, then A and B must be in equilibrium with each other. It sounds kind of obvious, right? But this simple rule is incredibly important. It's what gives us the entire concept of temperature. Next up, the first law. Now, this one is basically the law of conservation of energy, just dressed up for a thermodynamics party. Think of energy like money in a universal bank account. You can't just create it out of thin air, and you can't destroy it. All you can do is move it around or change its form. It's a strict energy budget for the universe. And this leads us to the golden formula, a huge favorite for examiners. Delta Q equals delta U plus delta W. So the heat you supply to a system, the delta Q, where does it go? Well, it has only two places to go. It either increases the internal energy of the system, the delta U, which basically means it gets hotter, or the system uses that energy to do work, delta W, on its surroundings. That's it. Simple, but so powerful. All right, now this is super important for your exams. This energy transfer we're talking about doesn't just happen in any old way. It follows specific paths or processes. And guess what? Most of the numericals you're going to face are based on one of these 4 key types, so pay close attention.
And here they are. This table is a real money slide. You might want to take a screenshot for quick revision. We've got isothermal, where temperature is constant; adiabatic, where no heat is exchanged; isochoric, where the volume is constant; and isobaric, where pressure is kept constant. See how for each one, the first law equation changes a little bit? Mastering this table is a game changer.
Okay, time for a quick pop quiz. Let's see if you were paying attention. In an isochoric process, remember, that's where the volume is constant. What is the work done? Take a second to think about it.
And the answer is 0, a big fat 0. Why? Because work done is pressure times the change in volume. So if there's no change in volume, delta V is 0, which means no work is done. It's a common trick question, so don't get caught out. Okay, so the first law says we can't create or destroy energy. But the second law is, in some ways, even more profound. It's the rule of nature that tells us what's possible and what's impossible. It dictates the direction of things, and it's here we find the real answer to that question about perfect engines. This is the famous Kelvin-Planck statement. I know, it sounds super technical, but what does it mean in plain English? It just means you can't build a machine that takes in some heat and turns all of it, 100% of it, into useful work. It's just not possible. Some of that heat is always going to be lost to a colder place. And that is why a perfect engine is a pipe dream. So if 100% efficiency is off the table, what's the next best thing? What's the absolute best we can do? To answer that, we have to talk about the Carnot engine. Now, this isn't a real engine you can build. It's a theoretical, ideal engine. It's the gold standard, the benchmark that sets the ultimate speed limit for efficiency for any real engine. The Carnot engine works in a beautiful 4-step cycle. It starts with an isothermal expansion, then an adiabatic expansion. After that, it undergoes an isothermal compression, and finally, an adiabatic compression brings it right back to where it started. The most important thing to know is that this whole cycle is perfectly reversible, and that's what allows it to achieve the maximum possible efficiency. And that maximum efficiency is given by this absolutely crucial formula. Write this one down, star it, highlight it. Efficiency, or eta, is equal to 1 minus T2 over T1.
Here, T1 is the temperature of the hot source, and T2 is the temperature of the cold sink. And listen up, this is super important. These temperatures must be in Kelvin. If you use Celsius, you'll get the wrong answer every single time. All right, let's do a super quick recap. For your exams, you absolutely have to know these three things. 1. The first law, our energy budget, delta Q equals delta U plus delta W. 2. The formula for an adiabatic process, PV to the power of gamma, is a constant. And 3. The ultimate efficiency limit, the Carnot efficiency, which is 1 minus T2 over T1. Master these, and you're in great shape. So, I'll leave you with a final thought to chew on. The formula tells us that the maximum efficiency of an engine depends only on the temperatures of the hot and cold reservoirs. So, what does that mean for engineers trying to build better engines in the real world? The bigger the temperature difference, the better the efficiency. Think about what that means for engine design. Pretty cool, right?
अगर वीडियो पसंद आया तो लाइक कीजिए, चैनल को सब्सक्राइब कीजिए और शेयर करके दोस्तों तक पहुंचाइए. All the best for your exams.